Top 10 gemstones that nature has already stopped making. Somewhere deep within Earth's crust, the forces that once shaped the planet's rarest gemstones have already come to a halt. Not temporarily paused, but geologically concluded. These aren't stones awaiting rediscovery in remote terrain, nor the byproduct of cycles yet to resume. Their formation has ended. Entire tectonic systems, hydrothermal networks, and volcanic chemistries have gone extinct, taking with them the only known conditions that ever produced these minerals. Each gemstone in this list bears the signature of a one-time event. The Earth does not replicate them. The chemistry is no longer active. The pressure fields have stabilized, and the source rock has gone inert. This documentary traces 10 such gemstones, each bound to a moment in geological history that cannot be repeated, and asks a question few collectors ever consider. What happens when nature stops producing something entirely? Don't forget to press and hold that like button, leave a comment, and hit subscribe before we begin. Ranked 10th, Ammolite, residue of a vanished ocean. Ammolite is the product of a biological epoch long erased. Its origin is not from rock, but from life, specifically the fossilized shells of Placenticorus and Hoploscophites, ammonites that thrived 70 to 75 million years ago in the Western Interior Seaway. This seaway, once stretching from what is now Alberta to the Gulf of Mexico, collapsed during the late Cretaceous as the Larimar orogeny uplifted the Rockies and drained the inland sea. What followed was a geological compression of calcium-rich sediments and iron-rich volcanic ash. Over time, these shells transformed into iridescent layers of aragonite microcrystals. Only a narrow band along the Bear Paw Formation contains ammolite in gem quality, approximately 30 meters deep, across a few dozen kilometers of southern Alberta. The conversion of organic matter into stable ammolite required precise conditions: low oxygen, minimal tectonic disruption, and uninterrupted burial. Those environmental circumstances no longer exist. Modern oceans contain different fauna. The sediment composition has changed, and the Bear Paw Formation is no longer accumulating organic detritus. The process is over. Commercially, ammolite was first recognized as a gem by the World Jewelry Confederation in 1981. Since then, regulated extraction by Proustite and other licensed firms has yielded limited quantities. Surface mining has already exposed the most accessible layers. Deeper excavation is geologically restricted due to the presence of unstable shale and the risk of collapse. Culturally, the Blackfoot and Kainai peoples referred to ammolite as Iniskim, buffalo stone, attributing it spiritual value long before modern gemology. Today, that association continues in controlled artifact reproduction, though genuine ammolite used for ritual purposes is rare and safeguarded by cultural custodians. No new ammolite is forming. The ammonites that created it are extinct. The seaway is gone, and the Bear Paw Formation no longer receives new sedimentation. Current production draws entirely from finite, fossil-bound layers. There is no replenishment, only exposure. As of 2025, remaining commercial reserves are projected to decline sharply within the next decade. Most gem-quality material is now held in private collections or protected under federal or indigenous conservation zones. There is no future supply curve for ammolite, only a residual archive of biological time. Ranked 9th, Painite, a crystallographic outlier in permanent stasis. No volcanic eruption produced it. No sedimentary basin harbored its growth. And yet Painite exists as a mineral that should not exist at all. The crystal was first recorded in the early 1950s by Arthur C.D. Payne, who acquired it in Myanmar's Mogok region, an area already famed for rubies and spinels. The specimen, initially mistaken for garnet, remained unremarkable in the British Museum until a routine spectrographic scan revealed its anomaly: an aluminum borate structure laced with zirconium and calcium. The boron alone invalidated the garnet theory. The zirconium made it stranger. It was, by every geochemical standard, out of place. Painite's composition reveals a paradox. It requires a boron-rich fluid phase, usually found in late-stage pegmatites, but must also form in the presence of zircon-bearing metamorphic rocks and under high temperatures. These low silica conditions are incompatible with most borate crystallization. These competing requirements mean that painite could only form where a boron-charged hydrothermal system infiltrated a marble terrain embedded with trace zircon under a rare and fleeting pressure-temperature regime. Myanmar's upper crust once hosted such conditions. Between 60 and 40 million years ago, during the early Himalayan tectonic uplift, magmatic activity in the Mogok metamorphic belt induced boron mobilization. Where this fluid encountered contact-altered limestones with the right impurities, painite crystallized in narrow fractures. But those geologic systems have long since cooled, sealed, and ceased to function. Subsequent deformation erased the reactive zones, leaving only fragments behind. For decades, only two-faceted specimens were known. Later discoveries in the 2000s brought the total count into the hundreds, but none were sourced from active growth zones. Instead, miners recovered them from weathered pockets and unconsolidated slope debris, evidence not of formation, but of residual erosion. No vein, pocket, or chamber has ever revealed a growing cluster of painite in situ. Attempts to synthetically reproduce painite have failed. Laboratory simulations have not recreated its crystallographic symmetry under controlled conditions, and thermodynamic modeling of the required elements shows near-zero probability of spontaneous recombination. The Myanmar government now restricts extraction from known painite zones. Most surviving material has been cataloged into geological archives, exported under mineral licensing, or secured in private museum-quality collections. The remainder is disseminated in fine fragments through gem auctions, each one tied not to a sustainable supply chain, but to a geochemical anomaly that has run its full course. Painite is not extinct, but it has no future tense. The crystal is finished, not in terms of volume, but in terms of process. Ranked 8th, Proustite, the light-sensitive relic of oxidized silver. Few minerals are as chemically unstable and yet visually arresting as Proustite. With its scarlet hue and semi-transparency, it has long been known among collectors as ruby silver, a name more poetic than scientific. But unlike rubies, Proustite doesn't form under heat or pressure. It emerges only under precise decay. When silver-rich ore bodies begin to oxidize at depth, releasing arsenic and sulfur into secondary circulation. The Atacama Desert in northern Chile offered one of the only naturally sustained environments for this reaction. In the 18th and 19th centuries, mining towns like Chañarcillo and Copiapó uncovered deep silver veins embedded in Permian-age sediments as these veins slowly oxidized over millennia, and only under partial atmospheric exposure. Rare sulfur sanides, such as Proustite, crystallized in secondary cavities. The mineral is, by definition, a product of depletion. It does not grow from creation, but from breakdown. Structurally, Proustite is a trigonal silver arsenic sulfide. With an unusually high refractive index and strong pleochroism, it is susceptible to light, often darkening when exposed for prolonged periods. A property that makes open-pit mining, storage, and even photography challenging. Museums around the world maintain it in closed drawers or dark boxes to avoid structural degradation. Unlike most gemstones, Proustite continues to react long after it has been extracted. Chile's silver fields, once among the richest in the world, have undergone significant changes. The oxidation zones that produce gem-quality Proustite have been mined out, and the deep primary veins no longer make the same chemical profiles. Modern industrial extraction focuses on bulk silver recovery through leaching and flotation processes, which can destroy delicate secondary minerals. What remains of Proustite is scattered, some in historical museum pieces, others in uncut crystal form inside sealed academic repositories. No modern geological process is reproducing it on a large scale. The mineral requires a partially open, high arsenic silver vein undergoing gentle oxidation, a condition that is environmentally unstable and geochemically short-lived. Attempts to simulate this in laboratory settings fail due to the compound's extreme sensitivity to light and moisture. Most of the world's finest specimens can be traced back to Chile's colonial mining history. New finds are anecdotal and fragmentary. Proustite's known sources are not dormant, They are geologically exhausted. In crystallographic records, it occupies a narrow window between chemical instability and mineralogical beauty, a compound that forms only during decay and disappears under observation. Ranked 7th, Jeremejevite, pressure frozen in pegmatite silence. In the Orongo Mountains of central Namibia, weathered granite domes rise above ancient lava fields. Embedded within these plutonic outcrops are pegmatites, intrusive bodies that cooled more slowly than the rest. Most contain nothing beyond feldspar and quartz, but in fewer than a dozen, geologists discovered crystals of a barat aluminum silicate so structurally clean that they refracted like aquamarine and read like topaz. It was Jeremejevite, first described in 1883 and rarely seen since. Its formation is rare, not by chance but by boundary. Jeremejevite requires boron-saturated fluids infiltrating the final phase of pegmatite crystallization with precise pressure control and limited contamination from fluorine or lithium. This sequence occurs at the terminal end of magmatic evolution, a geochemical dead end where incompatible elements briefly gather before solidification. Most pegmatites worldwide never enter this phase. Even fewer remain stable long enough for large, fastable Jeremejevite crystals to emerge. The Namibian deposits that produce transparent specimens are thought to be between 130 and 150 million years old. Their host pegmatites are no longer active, and the hydrothermal pulses that once fed them are extinct. Surface weathering now dominates the geology. Crystal pockets, once pressurized chambers, have collapsed. In most cases, only loose fragments or partially embedded crystals remain, and even these are heavily protected by erosion zones, wildlife conservation laws, and restricted mining permits. Outside Namibia, only trace occurrences of Jeremejevite have been recorded in Russia's Lake Baikal region and the deserts of Tajikistan, but these yield microcrystals unsuitable for gem use. None have matched the clarity or size of the Orongo material. No secondary source has appeared. Commercial extraction is impractical. Most of the gem-quality material was recovered during artisanal fieldwork in the 1970s through the early 2000s. Since then, local operations have shifted to aquamarine and tourmaline, and the remaining Jeremejevite sites are deemed economically unviable for scaled recovery. The mineral's hardness and lack of cleavage make it ideal for fast seeding, but its scarcity places it outside the reach of mainstream trade. The crystal's internal structure remains intact, but its geologic origin has gone silent. No active pegmatites are currently producing Jeremejevite. No new geochemical models predict its return. The fluid pathways are closed, the boron is gone, and the pressure that once brought it into being has long since dissipated. In field terms, Jeremejevite is concluded. In gemology, it's indexed, and in geology, it is categorized as terminal, a substance whose conditions of origin no longer exist. Ranked 6th, Alexandrite, the metamorphic window that sealed itself. Not all mineral formation is explosive. Some require prolonged compression, transformation, and mineral exchange at the atomic scale. Alexandrite, the chromium-rich variety of chrysoberyl, did not crystallize from molten rock. It formed beneath it. In the central Urals of Russia, where the Earth's crust once folded beneath Paleozoic seas, a narrow corridor of mica schists and serpentinites traverses a chromium-bearing ultramafic belt. Under sustained metamorphic heat and pressure, aluminum-rich fluids infiltrated these host rocks, and in the presence of trace chromium ions, chrysoberyl took shape. In rare cases, Alexandrite formed, displaying a unique optical response to different wavelengths of light due to chromium substitution within its lattice. This formation required three concurrent factors: a beryllium-bearing fluid source, access to trivalent chromium, and precise thermal pressure over time. It is a metamorphic anomaly, not a product of volcanism nor sedimentary pressure, but of long-phase mineral exchange at depth in a geologically active zone that no longer functions. The Tokovaya deposit, located near Sverdlovsk, was discovered in the early 1830s and proved to be the most productive. It yielded gem-quality Alexandrite with dramatic color shifts from emerald green in daylight to purplish red under incandescent light, a phenomenon that defined its mystique. but the original mining shafts were shallow. By the late 19th century, the richest sections were depleted. Attempts to reopen deeper zones in the 20th century faced both geological instability and diminishing returns. Today, the mine is closed. Modern occurrences of Alexandrite have been found in Brazil, Sri Lanka, and parts of East Africa. But these are the result of different geological histories. None replicates the specific matrix or metamorphic environment of the Ural stones. The optical quality differs, the color zoning varies, and the crystal habits are distinct under microscopic analysis. There are no active metamorphic zones in the Urals currently producing Alexandrite. The region's tectonic uplift has stabilized. Hydrothermal flows have ceased. Chromium mobility in the host formations has dropped below the threshold for gem formation. Alexandrite from Russia is not rare because it is old. It is rare because its specific process has come to an end. What survives is archival, in royal jewelry, museum collections, and geological registries. The stones may remain. The conditions that created them do not. Ranked 5th, Larimar, a surface artifact with no subsurface echo. In most gemstone classifications, there is an implicit assumption that what is found at the surface reflects a deeper system. Whether hydrothermal or magmatic, economic geology typically depends on vertical continuity, that seams run deep, that pipes extend, that there is more to be found below. Larimar broke that model. Found only in a confined region of the Dominican Republic's Barahona province, Larimar exists within weathered basaltic rock formed by ancient submarine volcanism. Its chemical structure, a copper-bearing sodium-calcium silicate, places it within the pectolite family, but its coloration and distribution isolate it entirely from the group. The blue hues come from divalent copper substitutions, embedded in hydrated microfibrils that only stabilize under low oxidation, low silica conditions. A set of parameters that occurred for a limited time in a single eruptive sequence millions of years ago. Despite efforts to find parallel systems in other volcanic islands, no analog has emerged. Larimar does not occur in the neighboring Antilles or global basalt provinces with similar age and mineralogy. Its confinement is not economic, it is geochemical. The basalt that hosted Larimar is no longer reacting. Its cavity systems, once saturated with mineral-rich fluids, are now sealed and dehydrated. Thermal imaging has revealed no heat flow. Geochemical assays show no evidence of copper migration. What once functioned as a low-temperature, hydrothermally active system is now inert. Much of what has been extracted came not from deep veins, but from shallow cavities, some barely a meter below ground. No parent structure has ever been identified. No feeder dike. No known vent complex. Core samples taken below the host layer show only unaltered basalt, devoid of any trace of copper-bearing mineral assemblage. In geophysical modeling, Larimar is not a vertical system. It is a crustal surface film, a rare chemical bloom that did not extend beyond its brief geologic moment. Mining continues, but the constraints are physical. Tunnels are narrow, unstable, and unventilated. Artisanal miners descend with basic tools, exposing small pockets that rarely yield high-grade material. Water intrusion is frequent. Structural collapse is common. Recovery rates are falling. Government regulation has slowed mass removal, and reserves are no longer easily accessible from surface zones. Petrologically, the origin of the stone remains a matter of debate. Some argue for late-stage hydrothermal deposition. Others suggest secondary alteration via oceanic groundwater. No model accounts for both the purity of Larimar's blue tones and the absence of larger chemical halos around the deposit. It appears to be isolated not just in location, but in mechanism, a reaction that occurred once, briefly, and never again. There is no evidence of renewal, no signs of ongoing mineralization. The system is geologically sealed. If Larimar reappears in future studies, it will likely be through reclassification rather than rediscovery. As it stands, the stone remains singular, not because it was hidden, but because there was never more beneath it. Ranked 4th, Benitoite, crystallized in an orphan subduction zone. The majority of blue gemstones owe their color to familiar elements, including iron, copper, and titanium. Benitoite does not. Its vivid sapphire blue luminescence, visible both under daylight and shortwave UV, originates from trace amounts of barium and titanium locked within a framework of silicate rings. No other gemstone shares its crystal system, its optical behavior, or its geological setting. That setting, now silent, existed for a limited window in the tectonic history of coastal California. Benitoite was first discovered in 1907 at the headwaters of the San Benito River. The stones were misidentified as sapphires, but their crystal morphology defied hexagonal symmetry. Within a year, mineralogist George Louderback confirmed that they represented a previously unknown mineral species, a barium-titanium cyclosilicate, crystallizing in the rare detrigonal dipyramidal system, space group P6C2. More striking than its structure, however, was its context. The gem formed in a hydrothermally altered portion of a subduction complex, a melange of serpentinized peridotite, blue schist, and natrolite veins. This was no conventional pegmatite or volcanic system. The pressures and fluid compositions involved were possible only at a precise temperature depth profile, where ancient oceanic crust was being pushed beneath the continental plate during the late Cretaceous. Benitoite crystallized in natrolite-filled fractures within partially metamorphosed silica-deficient host rock in the presence of barium leached from decomposing feldspars, a reaction path not currently observed in any active subduction zone on Earth. The only known source of gem-quality benitoite is the Benitoite Gem Mine near Coalinga, California, a site covering less than 1 square kilometer. Despite sporadic claims in Japan and Arkansas, no other location has produced crystals of comparable size, color, or fluorescence. The mine operated commercially for much of the 20th century but ceased full-scale extraction decades ago. Access is now restricted to limited surface collection under controlled permits. All primary hydrothermal conduits are exhausted. Deeper exploration has yielded no new primary zones. Scientific surveys using fluid inclusion analysis and isotope mapping suggest that the mineralizing event was episodic, shallow in extent, and short-lived, likely linked to the waning stages of a shifting tectonic plate boundary before the formation of the modern San Andreas Fault. Once that window closed, so did the chemistry. Attempts to synthetically grow benitoite in lab conditions have failed to replicate its color zoning or birefringence. The interplay of high-pressure metasomatism and low-silica host interaction has proven too complex for artificial modeling. Today, the state of California classifies benitoite as its official gemstone, but the source is no longer geologically productive. There is no evidence of new crystallization, no indication of residual hydrothermal flow, and no alternate tectonic regime capable of recreating its formation pathway. Benitoite's structure remains measurable. Its chemistry is well documented, but its environment, chemically specific, thermally narrow, and tectonically orphaned, is gone. Ranked third, Tanzanite, isolated by time, not distance. No other gemstone has a tighter geologic address. Tanzanite forms within a corridor less than 8 square miles in northern Tanzania, a zone bordered by graphite gneiss to the east and quartzite ridges to the west. This is not a deposit with potential extensions, nor a region underexplored. It is geologically final, a single lens of vanadium-bearing zoisite altered under the specific pressure and temperature of a long-dead orogenic event. The mineral itself, a blue to violet pleochroic variety of zoisite, is not rare in chemical terms. Zoisite is a common silicate, but the Tanzanian material formed under such specific constraints that it does not occur anywhere else in nature. The parent rocks date to the Neoproterozoic, but the critical alteration occurred during the Pan-African orogeny, when microcontinental collisions compressed and rotated pre-existing mineral bands, injecting vanadium into the crystal structure under peak baric conditions. This tectonothermal window has since closed. The material is mined from 4 blocks designated A through D within the Marilani Hills. Despite decades of extraction, all confirmed Tanzanite formation exists within a single stratigraphic unit known as the main horizon. Attempts to locate productive equivalents at depth or in nearby belts have failed. Magnetotelluric imaging shows no parallel zones. The mineralized seam dips steeply and terminates against a basement thrust. It does not continue beneath adjacent terrain. While Tanzanite can be heat-treated to intensify its color, a practice now disclosed in the ethical gem trade, its formation cannot be accelerated, mimicked, or extended. Laboratory efforts to grow vanadium zoisite have produced only opaque, structureless grains. The original geological pressure regime is no longer present anywhere on Earth, and the host rocks outside Tanzania lack the vanadium saturation required for substitution. In policy terms, the Tanzanian government has declared Tanzanite a strategic national resource. Large-scale export of rough stones is restricted, and state-owned entities regulate production volumes. Nonetheless, estimates suggest that over 80% of accessible, high-quality material has already been removed. Remaining pockets lie at greater depths, within zones of increasing instability and decreasing yield. No tectonic system is forming new Tanzanite. The metamorphic complex responsible is not only finite, but it is also concluded. The pressure gradients have normalized, and the chemical mobility required to initiate vanadium-rich recrystallization is no longer present. Tanzanite's future is not geological. It is both politically and commercially oriented. Its origin is resolved, its recurrence is excluded. Ranked second, Red Beryl, a volcanic anomaly with no parallel zone. Geologically, Beryl is not uncommon. Variants such as emerald and aquamarine form under conditions broadly distributed across the Earth's crust. Red Beryl does not. Its formation is so narrowly constrained, chemically, thermally, and tectonically, that it has been documented only in a single geologic setting, the topaz-bearing rhyolite flows of the Thomas Range and Wawa Mountains in western Utah. Red Beryl does not crystallize in pegmatites or hydrothermal veins. Instead, it grew within gas cavities in volcanic rock. Rhyolite that erupted 20 to 30 million years ago and cooled slowly enough to permit vapor phase mineral growth. These cavities allowed beryllium vapors to combine with manganese and aluminum under low pressure and moderate temperature conditions that are no longer active in any known volcanic province. What sets Red Beryl apart is its substitution of manganese, missing 3+, into the beryl lattice, a rare oxidation state requiring delicate redox balance. Too much heat and manganese oxidizes further, yielding colorless or yellowish beryl. Too little, and no incorporation occurs. The exact thermodynamic window lasted only during the final stages of gas exsolution within a rhyolitic cooling body, a process not reproducible in current geological systems. Despite isolated reports of trace red beryl in Mexico and New Mexico, no location outside Utah has yielded gem-quality crystals. And even within Utah, only the ruby-violet claim in the Wawa Mountains produced transparent material suitable for faceting. The deposit is shallow, spatially isolated, and chemically sealed. Exploration drilling beyond the known cavity zone has revealed nothing but barren rhyolite. The host rock is welded and chemically inert. It does not fracture or leach like granites. There is no vein system. There is no deeper reservoir. The crystallization occurred in a closed volcanic chamber whose structural integrity is now completely static. No magma remains. No fluid pathway is active. From a mining perspective, Red Beryl presents diminishing returns. Manual extraction is slow and dangerous. Most crystals are under 1 carat. Large inclusion-free specimens are scarce and were mostly recovered in the late 20th century. Since 2001, formal mining has halted. Ownership of the original claim has changed hands multiple times, but no new supply has entered commercial markets in meaningful volume. Red Beryl's scarcity is not due to over-extraction or protection policy. It is a matter of terminal formation. The rhyolite is frozen. The vapor phase window is closed. The elemental balance has shifted. There is no prospect for replication. Not in nature, not in laboratory conditions, not through synthetic analogs. It remains the only beryl variety whose geological preconditions are extinct. Its chemistry is understood. Its formation is mapped. Its recurrence is not under consideration. In first place, Trapiche Emerald, structural segregation in a sealed tectonic fold. There are emeralds, and then there are Trapiche emeralds, a mineralogical subtype so distinct in internal symmetry, so geologically restrictive in origin that only one region has ever produced them with crystalline regularity: the sediment-hosted emerald zones of Muzo, Colombia. A Trapiche emerald is not defined by hue or transparency. Its identity resides in its structure, a fixed six-point radial pattern radiating from a central hexagonal core, segmented by dark carbonaceous spokes. This isn't growth zoning, nor a surface optical illusion. The star-like geometry is real. Boundaries of inclusions locked between sectors of emerald crystallization that developed under rhythmic environmental interruption. These interruptions must be both forceful and precisely timed. The Trapiche structure forms exclusively in black shales that have undergone metamorphic adjustment within a tectonic shear zone. In Muzo, this occurred during the late Cretaceous, when hydrothermal fluids saturated in beryllium and chromium migrated through faulted sedimentary layers, exploiting microfractures in bedding planes. The pressure regime was dynamic but limited in scope. Crystallization began, then paused, then resumed, each time leaving behind a zone of non-Beryl inclusions that now serve as structural divides. The black spokes within Trapiche emeralds are not contaminants. They are the mineral record of mechanical pauses, organic-rich inclusions like albite, dolomite, or bituminous matter that filled the intersectoral spaces before the emerald regrew. This process required oscillating fluid delivery, alternating tectonic stress, and an uninterrupted crystallographic plane over thousands of years. Such conditions are not rare in general, but their alignment within a chromium-rich, beryllium-saturated environment is globally unique. The Muzo belt no longer maintains these conditions. Modern tectonic pressure is low. Fluid mobility has dropped. Chromium availability within host shales has been depleted through both natural leaching and historic overmining. No other locality, not even Colombia's own Chivor or Coscuez zones, has reproduced the precise combination of pressure, timing, and chemical stability required to create proper Trapiche symmetry. Imitations have emerged, partial zoning, six-fold inclusions, but none meet the mineralogical definition established by crystallographic analysis. Scientific sampling of active veins in Muzo over the past 2 decades has shown a declining incidence of Trapiche patterning. Massive Beryl formations or irregular tabular growths now dominate modern production. The narrow temperature pressure field that facilitated radial segregation no longer persists in active zones. From a mineralogical standpoint, Trapiche emeralds are not simply rare. They represent a single solution to a multivariable system whose boundary conditions have collapsed. There is no lab protocol to mimic mechanical inclusion during phased Beryl crystallization. No experimental pathway to stage fluid arrest cycles with sufficient spatial fidelity. Even in gem synthesis, Trapiche geometry remains out of reach. Trapiche emeralds are no longer forming, not because the mine is closed, but because the structural logic that built them has resolved. Each of these gemstones carries more than rarity. They represent geologic endpoints, the final output of systems that Earth no longer sustains. Some were the result of fault-controlled mineral saturation. Others formed under chemical or tectonic thresholds that have not reappeared since. Their scarcity is not a matter of market or politics, but rather a result of finished processes. While specimens may still circulate through private collections and scientific archives, the minerals themselves are no longer forming. And that distinction matters, because it shifts the question from where can we find more to what can their presence still teach us. Not about value, but about time, conditions, and the narrow windows that once allowed the impossible to crystallize. In geology, absence has a structure. These gemstones define it. Let us know which one resonates with you in the comments, and don't forget to like and subscribe to our channel for more content like this.